width is equal to 75. The depth, which is T, okay, the depth, which is equal to TF, and TF is 11.8. Let me confirm. Yep, 11.8. And then the Y bar, okay, so this is our Y axis. This is our X axis. Right, so the Y bar is equal to D divided by 2.205 divided by 2, or 205 divided by 2, minus by 11.8 divided by 2. Okay, 11.8 divided by 2. So this will be equal to 205 divided by 2 minus 11.8 divided by 2 times by 11.8 times by 7 point, or not 7.5, times by 75. So it's equal to 85.491, okay, times 10 to the power 3 millimeter cube, okay, or it's equal to 85.491 times 10 to the power minus 6 meter cube. Okay, so from here we can calculate our shear. Okay, Zx, so it's equal to 25 times 10 to the power 3. Okay, again, it's a wide flange analysis. Okay, multiplied by 85.491 times 10 to the power 3. Then we're going to divide by IZZ, which is equal to 40.9 times 10 to the power minus 6. And then the thickness is 11.8 times 10 to the power minus 3. So this will be equal to 25 power 3 times 85.491 power minus 6. Sorry, this should be minus 6. Divided by 40.9 power minus 6 divided by 11.8 power minus 3 is equal to 4.42. Come on, I did not calculate the stress for the previous one. It's okay. So this is equal to 4.428 times 10 to the power 6 Pascal. And if you look at the shear flow direction, is going towards the left. Okay. Now I realized that I did not calculate this value over here. Okay, the Vx. Okay, so if I were to calculate the Vx, okay, so shear xz is equal to Vx, which is equal to 16 times 10 to the power 3, multiplied by Qy, which is 40.268 times 10 to the power minus 6, divide by Iyy, which is 9.01 times 10 to the power minus 6. And then the thickness is 11.8 times 10 to the power minus 3. Okay. So this is for our Vx. Okay, so this is for this. I don't know why I forget to calculate. Okay. So it's 16 power 3 times 14.268 power minus 6 divided by 9.01 power minus 6 divided by 11.8 power minus 3 is equal to 16 power 3 times by 40.268 power minus 6 divided by 9.01 power minus 6 divided by 11.8 power minus 3 is equal to 6.06 times 10 to the power 6 Pascal. And if you were to look at this direction, is going towards the left, right? And if you look at the 25, is going towards the right. Okay. So now if we were to draw it as an element in terms of shear, how does it look like? Okay. So now I'm going to sketch the element A out. Okay. This is our element A. So we got one shearing stress going in this direction. Right? We have one shearing stress going in this direction at 6.06 times 10 to the power 6 Pascal. And this is due to Vx. Okay. We have another shear direction that is going down this way, right? Going down this way. And is going at 4.428, right? So the actual shear over here, so shear xz will be equal. So this is the direction we know that will be dominating. So it's 6.06 times 10 to the power 6 minus by 4.428 times 10 to the power 6. Whether is it plus or minus, I've drawn this direction to be positive or to be the plus. So this is equal to 6.06 plus by 6.06 minus 4.428. So it's 1.6, our shear is at 1.632 times 10 to the power 6 Pascal. Okay. So that is for element A. Okay. Now element B is not that difficult. Why element B, right? If we were to, so that is for element A. Okay. So now if we were to look at element B, right? Element B is not, the calculation, we don't need to do so much, okay? So if we look at element B, right? For this case, it's equal to what? 0, right? Okay, so now I'm going to do element B. Let me get rid of this. Right? So I'm going to copy this diagram over here. So we are now going to focus on element B. So we know that at element B, so we are going to deal with Vx is equal to 16 times 10 to the power 3 Newton. And element B is on the terminal, or is at the terminal. Therefore, Q, which is equal to 0, the shear stress is equal to 0, due to Vx is equal to 16 times 10 to the power 3. Okay, now we know that. So the next one, we're going to look at Vy. And you have to be really careful down here. Vy is not equal to 0 because Vy, it will be at its maximum value. So from here, we go over here. And let me undo phase 2 close. So Vy, right? So now, copy the wrong thing. I copy the wrong thing. Wait. No, I copied the right thing. Only Vy. Hey, yeah, probably I copied the wrong thing. Yeah, sorry. Let me do it again. That's better. So now we are going to focus on Vy. Which is equal to 25 times 10 to the power 3, right? So I'm going to make that table again. Okay, so I'm going to use this table again. So the formula that we're going to use, right? So now if you look at how the shear direction is going, the intersecting plane is Z, the shear flow is in the Y direction. So this is equal to Vy over Ixx Qx over T. Okay. So we know that Ixx on the table is equal to what? Ixx is 40.9 meter 4. And now the thickness is what? You have to be careful. It's the thickness of the web. So thickness of the web is 7.2. Okay. Thickness. Okay. So it's 7.2 millimeters. Okay. So we also know our Vy. So again, we have to calculate Qx is equal to width, depth, y bar. So we know the x-axis is of interest. That's a width, that's a depth. So let's calculate Qx. Okay. So the width of the flange. Okay. So BF is equal to 166. The depth, the thickness is equal to TF. Down here is where you have to be careful. Okay, 11.8. And then the Y bar, right? The Y bar now is equal to D divided by 2. D is 205 minus by 11.8 divided by 2. Okay. So this over here, right? One. This over here is for the flange. Okay. So this term over here is for the flange. Then you have to plus. Okay. So the width now is equal to our TW, which is equal to 7.2. Okay, so that's the width. The depth, so it's D divided by 2. D divided by 2. D is what? The depth D, 205 divided by 2 minus by TF. So TF is 11.8. Right, 205 divided by 2 minus by TF, which is 11.8. And then we do the same thing. So this is width, depth, Y bar. So this is 205.2. Okay, so this is 205 divided by 2. Minus by 11 point. Wait, Y bar is 205 divided by 2. Sorry, not minus, is plus by 11.8 multiplied by half. I'm using the standard form, okay, or the formula that we calculate the centroid now. So this is for the wait. Okay, so from here we have 205 divided by 2 minus by 11.8 divided by 2 times by 11.8 times 166 is equal to 189.22 times 10 to the power 3 plus 205 divided by 2 minus 11.8 times by or 205 divided by 2 squared minus by 11.8 squared times by 5 times by 7.2 is equal to 37.3 0.21 times 10 to the power 3. So this will be equal to, now we are calculating. So this is so 11,166 times by 11.8 times by 205 divided by 2 minus 11.8 divided by 2. Okay, I'm just going to calculate the final value. I know I'm getting late. So this is equal to 266 or 226.541 times 10 to the power 3 millimeter cube, or 26.541. Okay, so from here we directly calculate our shear. We have all the values. So By is equal to 25 times 10 to the power 3, 226.541 times 10 to the power minus 6, divided by 40.9 times 10 to the power minus 6, and the thickness is 7.2 times 10 to the power minus 3. Okay, so 25 power 3 times 226.541 power minus 6 divided by 40.9 power minus 6 divided by 7.2 power minus 3 is equal to 19.232 times 10 to the power 6 Pascal. Okay, so I'm going to stop here. So these are the stresses, shearing stress acting for element B. Okay, that's the case. Thank you. I'll still stay behind if you have any questions.
Eugene,
Yes.
when you did the